Hello, everyone. My name is Linyan. I'm a postdoctoral researcher at the University of Leeds in the UK. The paper I will be presenting today is titled Toward Sensorless Interaction Force Estimation for Industrial Robots Using High-Order Finite-Time Observers. In many applications, robot manipulators need to contact with environments, and thus the treatment of interaction forces is vital. Usually, interaction forces are measured by a force sensor. However, the high price of force sensors restricts their applicability in various settings. Moreover, the deployment of force sensors per se also increases the difficulty of structural design. Therefore, an efficient and easily implemented interaction force observer has great potentials. The dynamic model of robot manipulator is given by equation 1. By defining state x1, x2, x3, we can rewrite equation 1 into equation 2. Here, x3 is the interaction force which needs to be estimated. Then, we design the HOFTO as shown in equation 4. The specific solution steps are as follows. We first build the dynamic model of industrial robots by the parameter identification method, and subsequently design the high-order finite-time observer to estimate the interaction forces. This is my experimental setup, which consists of a motion control unit, a saw drive unit, and a basic machine unit, where the motion control unit is implemented by a back-off controller and developed in the MATLAB Simulink environment through a model-based design method. The saw drive unit is governed by a motion controller using the EtherCAT protocol. The basic machine unit is composed of 6 joints and equipped with a 6G force torque sensor attached at the end effector of the robot. The developed languages include MATLAB Simulink, PLC, and C++ on the back-off Tinker 3. Here we run the robot with the excitation trajectory. This is the performance of the identified dynamics model on an excitation trajectory, where the blue curves denote the real torque inputs over the course of executing the excitation trajectory, while the red curves correspond to the estimated torque with the identified dynamics model. You can see from the arrow curves that the identification is satisfactory. In order to evaluate the accuracy of force estimation, we consider a tracking task. Here is the corresponding 3D trajectory. Here are the X, Y, and Z components of the desired Cartesian trajectory, and the corresponding desired joint trajectory is determined by using the Jacobian-based inverse kinematics. Note that the most challenging situation for interaction force estimation is when some joints are unchanged or at ultra-low speeds. Hence, the first joint is almost altered, which leads to a challenging situation for interaction force estimation. The estimated interaction forces by using the HOFTO, the extended state observer-based and the disturbance observer-based methods are shown in this figure, where the real measured torque by using a torque force sensor is provided as the ground truth. It can be seen that the HOFTO method indeed has a more precise estimation compared to ESO-based and DUB approaches. We evaluated the proposed interaction force observer in colliding detection. Colliding detection is a very common task in industrial scenarios. In the event of a colliding, it's often required to detect external conductor forces. In our experiment, we broke the end effector of a robot when it collides with an obstacle. During the colliding, The response curves of the interaction force estimation in joint space and Cartesian space are shown in these figures, respectively, from which we can observe that the proposed estimation strategy detects the external force effectively. We also evaluated the proposed interaction force observed in the sensorless drug and teaching function by using the impedance equation. In the procedure of traction, the estimated conductor forces along the x and y directions are shown in these figures, respectively. Note that the chattering shown in these figures results from two main factors. First, the proposed interaction force observed is essentially a non-smooth and nonlinear observer, where the chattering is caused by the parameter and adjustment, especially the fraction power term. Second, measurement noise is a chattering-producing factor that cannot be ignored. Here, we will present some conclusions. We showcase a novel interaction force estimation scheme capable of estimating the interaction forces for industrial robots in the absence of force sensors. Estimating the interaction force is more precise than extended state observer and disturbance observer, and achieving Finite-Time convergence. Thanks for your attention.